Hi everyone. We're going to use Excel to find the probability distribution table corresponding to this histogram. Remember, the distribution we're dealing with is a binomial distribution with parameters n equals 10 and p equals 1/2. So a classic example of this is if we're flipping a fair coin 10 times. The probability of heads is 1/2 and we have 10 trials. The most likely number of heads is what? It's 5 heads, and that's why the bar there is highest. And notice that because we have a fair coin, p equals 1/2, we have symmetry about that middle bar. So when we do the table, we should see these properties. P of 5 should be highest, and we should see symmetry about p of 5. And lo and behold, if you use Excel, that's what we get. Imagine flipping a fair coin 10 times, count as successes heads. Let x be the number of heads on the 10 flips. So here's the binomial table, where x has a binomial distribution, where n equals 10 and p equals 1/2. We have a fair coin. How many heads can we get? Anywhere between 0 and 10, integer. Notice the probability of 5 heads, p of 5, is the highest among these. It's about 25%. Notice that p of 4 is equal to p of 6, about 21%. Notice that p of 3 is equal to p of 7, about 12%. We have symmetry about p of 5. It's very unlikely you'll get no heads or all heads. And the probabilities here add up to 1. That's the sum. That must be true of any probability distribution table. All right, now let's say that you wanted to find p of 5 in particular. Well, remember there was the old binomial formula from before. We could use Excel, find the probability that x, the number of heads, is 5, where x has that binomial distribution. The command is binom.dist. X equals 5, that's the number of successes or heads you're looking at. N equals 10, that's the number of flips or trials. P equals 1/2, that's the probability of heads, a success. And we put false here because we want a particular probability, not a cumulative probability. If you put true, then you get a cumulative probability, meaning you get the probability that x is, say, less than or equal to 5. Then you get the sum of these probabilities here. We want individual probabilities, so we make this false. If we put that in, equals binom.dist, x equals 5, n equals 10, p equals 1/2, false. We want a particular probability. We get about 25%, the same number as over here. And again, these probabilities are seen as heights in this corresponding histogram. All right, so we know a lot about this distribution. And as I claimed before, of these 50 distributions, these 50 histograms, the only one that we counted as approximately normal was this one. And why is that? What are the assumptions under which we're going to allow a normal approximation for a binomial? When can we say that a binomial histogram looks normal? It's under these conditions. Conditions for using normal approximations to binomial distributions. We will use normal approximations to binomial distributions if and only if the following two conditions apply. If NP and NQ are both at least 5. Remember that Q is 1 minus P. It's the probability of a tail in our examples. Now, why does that make sense? Well, remember that of the 50 distributions that we saw, this was the only one that counted. The binomial, where n was 10 and p was 1/2. It was the most basic binomial distribution that can be approximated by a normal distribution. So as n gets larger, if you consider larger values of n, like n equals 100, n equals 1,000, and so forth, then more distributions, more histograms will count as normal looking. Of course, it helps to be close to 1/2 and not to be too close to 0 or 1. So normal approximations to binomials are more appropriate if the sample size or the number of trials, n, is large, and if p is pretty close to 1/2, or at the very least, if p and q are not too close to 0 or 1. So here's the idea. If n equals 10, you really need p equals 1/2 in order for this to count as normal. But if we were to do n equals 100 or n equals 1,000,000, then many values of p will work. Only the most extreme values of p and q would fail us. So if n equals 1,000,000, then p and q could be almost anything. It's just that p and q could not be too close to 0 and 1. And by the way, if p is too close to 0, then q is too close to 1, and vice versa. If p is too close to 1, then q is too close to 0. Ideally, we want values of p and q that are close to 1/2. But the greater n is, the higher n is, the more we can deviate from 1/2, 1/2. So this here represents a compromise. Here's the idea. When are we more likely to be able to use a normal approximation to a binomial? If n is big, and if p and q are not close to 0. Again, when are normal approximations appropriate? The larger n is, and the further away both p and q are away from 0. So if you have these two conditions applying, if np is at least 5, and if nq is at least 5, then that guarantees that n is big enough, and that p and q are not too extreme, so that neither one of these is too close to 0. So under these conditions, we will say that a binomial histogram looks about normal if np is at least 5 and if nq is at least 5. But what is the normal approximation we're going to use? We're going to see next time.